So that becomes our ER model. And once we have that, we've got our relational model set up. So we end up with a bunch of tables that look something like this, right? So we have here a student table that has social security number, first name, last name, emails. I've expanded on the attributes just to make it look slightly different. The students have multiple phones. Everybody has lots of phones, right? So we have, for example, Roberto Perez has 2 telephone numbers, lives or comes from San Francisco, all that kind of stuff, has 2 email addresses. People might have multiple email addresses, and all that kind of stuff. We have courses, and for each course we've got a course number and then data about the course. And the course data that I put over here, I've again added a few attributes, includes a room and the number of seats in that room. Okay, so we have here the room and the number of seats in that room. So this tells us that room 1127 has 60 seats. If you're alert, you'll already notice that I've sort of rigged this a little bit because this data is redundant. And we can see it has severe inconsistency issues. So for example, if I accidentally change this to 70, and I ask the question, how many seats are there in room 1127, then depending on whether I start from here in searching or I start from the back, I'm going to get a different answer. That's inconsistency, and we can see that's coming out of the redundancy that's inbuilt in this stuff here. And finally, we have a relationship table, which is enrolls in, and the relationship table has borrowed because that's a many relationship, has borrowed the key of the student table and the key of the course table. And then it has some other data of its own, the first name, last name of the student, and their grade. Okay, right? So that becomes our enrolls in table. Again, this is not meant to be a good database because I've sort of rigged it a little bit to make it make our next step a little bit more meaningful. But this is what is, it's not unreasonable, right, to have a bunch of tables that look like this. And this comes straight out of our ER model. So that's the goal here. And once we've done that, then we can say, hey, we've got our relational model. We have a bunch of tables, and SQL is going to work now in answering queries on these tables. So if necessary, we can use that. So that's where we are right now. Once we've got our relational model, we want to move on and normalize it. So what is this normalization stuff? Normalization is the process of reorganizing the database to reduce redundancies and increase integrity. That means increase the consistency of the data, okay? Make it more consistent. So the idea of normalization is it actually ends up making the queries a little bit more efficient and more consistent, which is kind of nice, all right? Because it's where we want to be in this kind of world here. But more importantly, what normalization does is it addresses 3 different types of anomalies that typically give rise to redundancies and inconsistencies in a database. So these anomalies are anomalies in the sense they are you can think of them as features of the database that will cause a problem when you're trying to insert data or change something or remove something from the database. That's why they're called anomalies, because they cause problems. So the problems occur when you're inserting new data into the database, or when you're changing a value in the database, or when you're deleting a piece of data from the complete data item from the database. And the whole purpose of normalization is to ensure that these anomalies are, at least the probability of having these problems is greatly reduced. Okay, that is the goal of this. It's a very complicated field, and typically it would require perhaps normalization alone would require a half semester of coursework. So what we're going to do here is do a very simple philosophical view of what normalization aims to achieve and leave it at that. Okay, so because this is a data analytics class, it's not a databases class. So we just want to understand the philosophy behind it. We don't want to be experts in this stuff here. So the first anomaly that we want to look at is the insertion anomaly, and this occurs when you want to add something to the database, but there is no place to add it. So you want to add some new information, a new entity or a new thing to the database, and you can't add it anywhere. Okay? You look at your table structure, there's no place at all to add it. So let's take a look at an example. So let's say we have a table here called professor, and the professor table has 3 columns: the name of the professor, the office where they sit, and their department. Okay, so here we got these three things here, and we got professors. This got a little bit messed up, but let's say there's actually a name over there. Professor Lee, Professor Wu, and two other professors, and their departments are over here, and that information is there. Now what happens is that the university decides that it needs a physics department. So it says, all right, let me add a physics department to my database. But initially, we don't have any faculty members. The Senate, University Senate has just sat down and had a meeting and said, all right, from now on, we have a physics department, and we're going to start offering physics degrees. We're going to start admitting students for a bachelor's in physics starting in the fall of this year, right? So now we have a decision to do that. We have have to set up the process of admitting students and doing all kinds of things. But the only place in our database where a department is mentioned is in this table called professor. If there's no professor in the physics department, we can't have a physics department in our database. There's no place for it. We can't add it to our setup because you can't just have a nothing, and physics. You need values over here and you need a value over here. There's no professor, so we can't add it, right? That's as simple as that. So this is what's called an insertion anomaly, because we have, and conceptually what's happening is that we have this real world thing called physics, right? Or real world thing called department or major or something, right? That is out there. But we haven't modeled it in our database as an entity. We modeled it as an attribute of another entity, right? We modeled it as an attribute of the entity professor. So though it's an entity which apparently now we can see has some importance of its own, we treat it as an attribute. So that's our problem. So there's no way to add it. So this is an insertion anomaly because now the Senate has said physics, and the computer science, IT department or whatever is sitting down and saying, hey, where do I put physics? I can't see anywhere to put physics. This is the problem, right? So we've got to solve that, and this is fairly easily solvable, because what you can do is you can take out, or what you would need to do is you need to take the department, and remember I said that the reason we're having the problem is because department is really an entity of some importance, and we model it as an attribute. So what we should do is make it an entity. So we make it an entity over here, and we have now industrial engineering and operations research, mechanical engineering, computer science, and we add a new department called physics, right? And we give them a code as a key, which is not necessary, but typically when you have long strings of this sort, it's a good idea to have a simple key attached to that, because you're going to repeat this in other places. So rather than having to put industrial engineering and operations research here, we can just use IEOR. Okay, that's the idea here. So now we've got this. So now we can add physics because we just added to the department. Nothing happens to professor. We don't have a new professor in that department. There's no one teaching in that area. So there's nobody there. So we don't need to add it there. We can just add it over here, and then if there's any other administrative stuff that needs to be done, it'll follow from this, right? If, for example, our brochures, the school bulletins or brochures, they list departments using this table. They list departments. They can just use this table and say we have a physics department. So what if we don't have any professors, but it's there? So we can either make a new relationship called, say, belongs to, and create yet another table that has each professor name, say Micha, IEOR, etc. Or we could simplify matters by just including the department as another column here, even though it's not typically no longer an attribute. But since this table is only going to contain just one column, and it's not a perfect solution, but it's for ease of access, it makes sense to say, hey, we'll just collapse the department right into this column over here, into this column inside our professor table, and our professor table now contains the department code for each department, and we can access the name of the department by following that code over there. Okay, so this really is a sort of, you can think of it as a synonym for a relationship, but we just collapse it into a single table. So that's the way to deal with insertion anomalies. And what you're really doing is you're saying that, hey, I have an entity that is modeled as an attribute, so I need to take it out, make it a separate entity, and build relationships between that entity and other things. Okay, that's the goal there.